microcontrollers with the help of Matlab code. And about inQbe, actually, we are, as we said, actually, that there is an R&D organization that is located in Cochin. We have a research space in Trust Research Park at CET. And we are having our project area, we are having some industrial projects. Mostly we are having some industrial projects in EV, mostly in motor drives and other power converters and inverters, and renewable energy and energy management, just like battery management and charging systems. And we do also supply some development systems, including development kits and solutions for the education institutions in different areas. Our main agenda is to discuss and hands-on and having hands-on hardware implementation of control for a converter. Actually, as the real interactive session, I expect questions in every point, every slide. You can ask questions. I'll try to answer by my best. And we'll have Simulink simulations, and we'll discuss about prerequisites for hardware implementation. What should we learn? What should we collect? And everything. And we'll discuss about Simulink code generation that we focus to deliver for the educational institution, because we have to implement our simulated algorithm to the hardware without the complexity of programming. And the live hardware examples will be there for Pwm Control experience. We'll have a small experiment from the simulation to hardware that can be implemented using the microcontroller for a closed loop control. I'll just brief about the EV charger that you had a lot of sessions. As we see in the picture, in Pwm sections of EV charger will contain different parts, including power factor correction and DC-DC converter and its control. As we know, most of the power, actually our topic is the EV charger and its influence, actually its impact in the grid. When we connect a charger to the grid, there will be a lot of challenges, including THD and power factor to the line, and some disturbance, including THD. So our Pwm circuits should have a capability of solve all these things, and should have proper sufficient efficiency to deliver the power without much loss. So for a basic circuit, I'm here showing only a single phase grid connected EV charger, unidirectional charger. So it will take power from AC source, 230 volt or 110 volt 50 hertz supply. So it should be converted to DC. Again, it should be again converted to DC-DC with isolation. And again, that DC voltage from the DC-DC converter, we can connect to the battery, and the charging voltage, current, and power quality should be controlled with the circuit. We can see that in first portion, we can see that there is a rectifier. It will convert AC to DC. As we know, when we connect a rectifier to the AC source, it will make heavy THD harmonic into the line if we use high value capacitor after a rectifier. That means if we need a ripple free voltage from the rectifier, we should have higher capacitors, higher value capacitors. It will inject heavy harmonic into the line. So we will have a small value capacitor after the rectifier, and we'll have a power factor correction circuit. Here it is a simple boost PFC. After this PFC, we will have a high value capacitor. It will give a steady DC voltage, less ripple DC voltage. So the power factor issue will be corrected by the PF correction circuit using a boost converter. In this part, we should have a control to shape the current from AC to DC conversion. That means from AC to DC conversion, that's not a simple matter when power is high, power quality is concerned. So there should be a power factor correction along with the control to achieve this power quality and ripple free voltage. Here we should have a control, even in single phase, we should have a current control to achieve proper current shape to reduce the harmonics. After that, we should have a DC-DC converter that should also have an isolation feature to avoid the electric shock. So in different application, different isolate mostly transformer isolated high frequency converters are used. In some cases, most cases, the resonant converters are used to reduce the loss and reduce the size. Here we are having a series resonant converter. For an example, we are discussing only a small converter. In this, we'll need, I am just pointing out the factor that we are going to discuss. That is, we will need controllers both in PF correction and DC-DC converter and the charger control. When we go for a three-phase converter, there should be a three-phase AC to DC converter with active switches rather than diode bridge rectifiers that is used to achieve the high power factor, low THT AC-DC conversion. In this application, we will have a DC boost converter to achieve the PFC. That I'm not going to discuss about the detail about PFC and DC-DC converter. I'm just discussing about the need of control. Here we should have a controller that is used for generating proper sinusoidal current and to make the controlled DC voltage on the VDC bus, independent of bus voltage variation in the line also. Even if line voltage is varied from 150 to 270 or something, 170 to 270 or something, the bus voltage should be stable. Say in this case, it can be set as 400 volt. So the PF correction circuit will also control the bus voltage. So there is two things to be controlled. One is input current shape and the bus voltage. So there should be a controller that is controlling two things: AC-DC conversion current shape and the bus voltage. And about the unidirectional series resonant converter, we may have the pulse shift modulation or pulse position modulation, or we may have the frequency modulation. All these should be applied by a controller, even if a frequency, because it is a series resonant converter, we will have a frequency modulation for controlling this converter. So frequency modulation should be applied from the digital controller. This should also can be done by the microcontroller or an Fpga. Here we are discussing about an Fpga only. This is the need of controller for the Pwm converters. So when we think from industry and academic side, actually we are having a lot of simulations and theories that this is discussing. All these things are already known to you. Just for information, I'm just listed here. But all these things, sometimes we'll discuss about the theory part and its waveform part. And next level, we'll go for a simulation. In some case, we'll terminate our experiments in simulation only. After that, we have to go for a hardware implementation. In hardware implementation, we'll need a Paltronic circuitry along with the controller part. In controller part, we'll have to write the code for the controller. Here we are discussing only on that part, how to generate the control part into the hardware. So we'll discuss about a converter, and we will just simulate a boost converter only, a DC-DC boost converter only, not PFC, a DC-DC boost converter, and we'll make a closed loop simulation. Roughly, we will make a closed loop simulation. After that, we'll try to implement into the hardware. We'll have a live hardware demonstration of this simple experiment. This is to realize and communicate how can we translate a circuit from simulation to the hardware with the help of a microcontroller. As I discussed, role of microcontroller and in EV charger, multiple converters, just a PFC and DC-DC converter, as we discussed. It will definitely need a controller that should have capability control for voltage and power quality. And user may have some set points, just like power value, voltage value, and all the things should be met by the controller, by the code or firmware. And there will be a program control algorithm, just like constant current charging, constant voltage charging, for example, and constant temperature charging, or any other charging algorithm can be tried with the microcontroller by having proper firmware. And there should be communication because it is a demand-based system. Actually, there will have demand from when we connect a charger from grid to vehicle, there will be a demand from the vehicle side, how much charge will be needed from the battery system. So there should be a proper communication from the battery system towards the Paltronic side. That should also met from the control part. And even from user side, there will be command to set the charger limits based on cost or power limitations. And all these parts, mostly microcontrollers are used for all these control parts. In some case only, in some high-speed applications, FPGAs are used. Anyway, even there are digital controllers and analog controllers. Microcontrollers are must thing. We will have a boost converter simulation. Actually, I am trying to discuss about a basic boost converter. All of you may now know about the boost converter, basic boost converter. I'll just discuss about basic boost converter, and I'll try to simulate a Matlab Simulink model. So after that, we'll have a closed loop control, a basic closed loop control. After that, we'll try to implement this basic closed loop control to the hardware by the help of a microcontroller. So I'll just start with a Matlab simulation. I hope that my Matlab Simulink window is visible to you. Please let me know if it is not visible.
Yes, sir, it is visible, sir.
Thank you. I'm just starting a basic boost converter. By adding basic components. All these are not to you, but just for a step from simulation to hardware. I'm just trying to implement a basic boost converter. I'm just giving rough values. In Pwm block and voltage measurement. I'm just giving a step value of 1 microsecond that we can discuss. Just simulating in discrete mode. You can add a scope. I'm just trying to simulate in 1 second. Just given value of 100 ohm resistor as load and 1 millihenry, and we have to add a pulse here. Just be adding a pulse generator of 20 kilohertz, and so I'm just giving the duty ratio of 50%. After a simulation, we can see whether there is an output. I'm just setting input voltage to 12 volt and duty cycle is 50%. Ideally, it should give a 24 volt. Now we are getting a voltage that is close to 24. There will be some drop due to switch drop and diode drop. We are not considering this now. Actually, when we need a control, actually we can consider this thing as a plant with some dynamics and other properties, and we can control its output voltage by just varying the duty ratio. I'm just varying the duty ratio only. All other things are fixed. We can see now output is close to 19 volt only. So output can be controlled, output voltage can be controlled. That output relation between, basic relation between the output and input is 1 by 1 minus t. V out and V in relation will be proportional to 1 by 1 minus t. That means V out will be equal to V in into 1 by 1 minus t, whether D is the duty ratio of 0 to 1. Here we have applied duty ratio in percentage only. Now I am adding a PWM generation. We are adding a basic PWM generation block a comparator, and a ramp generator. Here I'm just giving time values of 0 and 1 by 20 kilohertz and output of 0 to 1. Then you can give a value of D from 0 to 1. Here I am just giving 40%, that is 0.4. Just checking again. Now we are getting similar value that we have got using pulse generator block. Here I am trying to make it in a closed loop, simple closed loop. When we try to think just like this part as a plant, when this part is a plant, the plant control is the duty cycle and the plant output is voltage. So we can have a reference voltage, just like I am just trying to set 20 volt as the reference. I'm taking a difference block, just like this, and I'm just reconnecting these two output voltage. So here we will get error. All these are very common. I am discussing this to how we can implement these things to a microcontroller, a digital hardware. So I'm just giving its output to Pwm Block. So now it is plant, error, and controller. So now I'm just setting the PID controller as discrete block that I will discuss later. I'm just giving a rough value of AP and KA. And I'm just giving a limit because it is a boost converter. I'm just giving a limit of 70% to 0. We'll discuss about the other options of PID control. Now we are having a boost converter and a feedback and a reference voltage and error section, and a controller that is connected to the Pwm converter. Now the set voltage is 20. You can see that the output is getting near to 20. There is some oscillation that can be tuned by the controller. The voltage is near to 20 volt. Okay, so we are discussing about how to implement these things to hardware. When we go for hardware, we can see that in simulation we have used basic inductors, MOSFETs, diodes, and capacitors. All these can be realized as the same component, same electrical component in the hardware with proper voltage and current ratings. After setting up all this, we should have a controller and a Pwm generator. So I am taking this part, Pwm generator, out from this thing. So this part is the electrical part and this part is the overall control part. And this control part should be implemented in the microcontroller. That means when we go for hardware implementation, there will be at least two part. One is the pure electrical components, and second part is the firmware or software component that is used to control, that is written inside the microcontroller. So when we try to convert this to the program, we'll need a complex programming, complex programming steps when we are not aware of microcontrollers. Here I am just discussing about how to translate these things to the microcontroller or the control implementation. So apart from this, we'll need an ADC to read output voltage to the digital hardware. So we will use an ADC here. That means the voltage will be converted to digital using an ADC, which will be inside the microcontroller, and this part will be implemented using the Pwm Generator Block inside the microcontroller. That means we will use a controller that is mostly tuned for power electronics or drive and control application. That means I had several feedbacks from several experience from some experimenters. They have used basic microcontroller just like Arduino or basic PIC microcontroller for these things. In some cases, there are a lot of limitations. That means even some microcontroller will not have proper efficient Pwm generator blocks. That may be only single Pwm, not complementary Pwm may not be available. All these cases we will need a controller that is tuned for a power electronic control application. That will help us to implement all these things trouble-free and in efficient manner. So we will here we will discuss about Texas Instruments TI C2000 microcontroller family, and our control part will be translated into the controller using Matlab coder. Matlab coder will simply translate our control things to the code and it will dump into the hardware. I'll be back to the simulation after discussing these things. We have discussed about the boost converter simulation in Simulink, and we have added Pwm. Actually, I'll just brief off about the Pwm block. That's some in some cases that people were not aware about the Pwm blocks in the microcontroller, and in some cases, some people may use ramp and compare in these space. That may take some delay in execution. Actually, when we go for Pwm is a simple thing that's compare our signal, that means our pulse width value, to a linear ramp waveform, and it will generate pulses. Its width duty, otherwise that its duty ratio will be proportional to the input value. That's only the pulse width modulation. Usually that is implemented in older cases, that is implemented using sawtooth generator and op-amp comparator. That's a basic thing. So we can compare our signal with the sawtooth using a comparator. So it will generate a pulse. In modern electronics, it will be generated inside the microcontroller by having counters. Counter will count from 0 to a maximum value with maximum speed of the controller. That means with the clock speed, that means microcontroller execution unit is free from the Pwm generation. That means a dedicated block that's known as Pwm or counter block may be available inside the microcontroller that will generate a pulse width modulation. Here we will use a Pwm block inside the microcontroller. That means it needs high sampling rate to achieve proper time resolution. So here I just given discrete sampling time of 1 microsecond. in many cases there will be a lot of confusions for selecting the discrete sampling time. A discrete sampling time simply means all these in simulation, all these things are a model. It will be sampled with the discrete sampling time. That means discrete sampling time should be more than 50 times of the switching frequency to achieve at least 2% duty cycle accuracy. That means when we set discrete sampling time, sampling frequency, just like if we have 20 kilohertz switching frequency and sampling frequency of 100 kilohertz, so 5 times only. 5 times, in that case, it is 5 times. So it can generate only 20, 20%. That means 20, 40, 60, 80 steps. That means PWM resolution will be limited to 20%. That means only 20, 40, 60, and the multiple of 20 only can be used. That means when we use 500 KSPS, we'll have more time resolution. That means when we simulate the Pwm circuit in Matlab Simulink, we should set a proper discrete sampling time to achieve required conversion, required control accuracy. So in microcontroller hardware, it will have a high resolution. That means PWM, based on the switching frequency that we choose, PWM resolution can be very high. That means it can achieve very lower change. It can achieve very lower resolution.
Yes, sir.
Yes. Hello.
No, that was some noise from participant side, accidentally.
No problem. So we should set a proper PWM resolution. That means proper sampling time based on the application. In higher frequencies, there are a lot of challenges from the microcontroller side, because microcontroller clock frequency should be very high for the high frequency PWM generation. Here we will use a 60 megahertz microcontroller for this application. That's enough for this. And we have discussed about closed loop control. As we seen in the simulation, there will be a control part and a Pwm generator part that is to be implemented in the microcontroller. Here we can see different colors. We can see the feedback is red. That means the feedback is sampled at the highest sampling rate that can be used for the simulation. But for the control implementation, control frequency, control loop frequency can be lower than the switching frequency. So here we have reduced the sampling rate by a rate transition block that is shown here. And one second. Here it is a rate transition block. So it is down sampled by rate transition. So we can have a lower sampling rate for the control loop. Again, it is upsampled for the Pwm generation block to get the actual sampling rate for the control. So control loop frequency can be lesser based on the control algorithm design. In this, we will convert these things to the microcontroller by using the code generation feature from the microcontroller, Matlab to microcontroller. So we are having this one. So we will implement this part to the microcontroller. Electronic part already known to us, and control part is also known to us. We are discussing only how to implement this one to the microcontroller. So we will have a block like this. I'll discuss more about this part. Actually, this is taken from this one. There's a PID controller and a reference and a PWM block. I'll discuss more about this, and an ADC that is taking feedback from the output, and again that's I'll discuss more detail. Actually, this can be translated to the code by the features of the code generation facility from the Matlab Simulink coder. All these things will be converted into the code and can be downloaded into the microcontroller, and we will get a closed loop control as we simulated in the Matlab Simulink. So I will discuss more detail about this. After that, we will go for a hardware realization. I'll first discuss with the Pwm generator. Actually, when we try to implement this, it will implement in two ways. That is, one is the control loop will be implemented as the program. It will read voltage from ADC, and it will scale, and it will measure the error, and it will implement the PID by having proportional integral derivative control part, and it will make a sum, and it will give into the PWM block. But in PWM block, as I said, there will be a dedicated Pwm generator block, because in this Pid microcontroller cannot work. Only Pwm generation section only can give proper speed Pwm. So there will be Pwm generator block inside the microcontroller. Here we have installed Matlab Simulink block set for C2000 microcontroller. Here we are aware of this, and in Simulink additional block sets for different controllers are available from the Matlab side. So we have installed Texas Instruments C2000 support package for the microcontroller, and it can be used for generating this code. That means we have used common blocks just like PID and gain blocks from Simulink, and additionally we have used ADC blocks and PWM blocks that we have installed inside the Simulink. That is additional blocks we have installed. That's only things that we have to install for the code generation. This is very useful for academics and the R&D purpose, because there is time to market. That is, when we try to implement our academic or research purpose or R&D projects, it will need to implement in very less time to generate the output. In that case, there will be lot of benefits when we are going for Simulink block code generation. That means a machine, that means a Simulink coder will generate a code that is based on our Simulink thing, that is mostly well suited for the application. So it is very easy to use in academics. So I am just suggesting this to practice from the academics, to have a complex hardware implementation without having the programming complexity. So here we are discussing only a small example, but even if we need, currently we are implementing motor controls, inverter controls, and other renewable projects from the Simulink using the Simulink coder. And a lot of R&D, other R&D companies, R&D institutions are also using the Simulink coder. Here I'm just trying to open the Pwm generation block. In this, and this is only a settings block. That means in normal coding, we will configure all things of the Pwm generation block using special function registers. So we will set each registers by looking into the data sheet. After that, we will assign ones and zeros in each position. After that, we will give that binary code to the program, then it will be configured. But in here, we can configure these things by using a GUI block. From the GUI block, we can set PWM frequency here. I'm just given a PWM frequency of 20 kilo 1 by 20 period, then 20 kilohertz frequency can be generated. And this is a flexible enhanced PWM. Because of this enhanced PWM module, we will have a lot of features that I will discuss. So we have PWM A and B inputs that we can set the rules what should come when PWM A and B meets the counter. So I will explain with a figure after this. So by using this GUI block, we can generate PWM to the microcontroller. So in microcontroller pin, we'll get a PWM signal that can be controlled from the code blocks that's we are connected inside the Simulink block. Discuss about the Pwm generation block. Here we are having a picture that is a triangular wave that is generated. Triangular or up down counters can be used based on our PWM requirement. That means when we need a single PWM, we can use up or down, and when we go for multiple PWM with a central aligned, we can go for up down, that is a triangular wave. If we need only left or right aligned PWM, we can use up and down features. So here from the picture, we can see that the counter will start from 0 to PRD, that value only a PRD here. Then it will count down to 0 again. So in this point, we can see that there is two inputs for this block, that is compare A and B. In this, we can see that there are different events that needs compare A value to the triangular value. Then 0, then compare A value meets and B value meets when up count, when counter meets PRD, and counter CMB B meets when count down, and CMB A meets when counter. That means 1, 2, 3, 4, 5, 6 events are there. We can program those events. Actually, I will open the picture. We can program those events by using the GUI block. From the GUI block, we can decide what should happen in this case. I have set only clear and set clear. That is, I have used a complementary PWM with minimum features by setting clear set and set clear rule for CMB A and CMB A only. So we are having a CMB A input. That means we can give, here I have given counter compare units as percentage, and it is connected to an input port. Here we can give a value that is 0 to 100 based on the pulse width requirement we needed. That means when we need a 50%, here we can give 50% value. Here that we have connected to the PID controller. So we will start with a basic PWM control. I'll discuss about just hardware. This part we have an experimental hardware with a lesser power of 100 watt. Here this is a basic hardware block. It is having two MOSFETs. There is a synchronized boost converter, and its other components like inductors, capacitors, and all. And we have a driver circuit also. In this, we can give pulses from the microcontroller. with 3.3 volt input, and we can take a feedback from connectors for voltage feedback. We have connected all these to the microcontroller board that we are having, TMS P20 28027 development board from inQbe. Actually, this is connected to the PC via JTAG emulator that is connected to the USB port. And control will be implemented like this. From ADC, we'll discuss more about ADC. From ADC, we will read voltage from outputs, and it will generate an error, and it will be compensated by the PID controller, and it is connected to the Pwm generator. So a closed loop control will be realized. Actually, we are just giving control block from Simulink, and it will generate sufficient code that we can discuss about the code. Will generate sufficient code from these blocks, and it can be dumped into the microcontroller. So we will get a controlled hardware with the proper designed output from the Simulink. So we will start, we'll take a small break. After that, we will start with the hardware. We'll set up the hardware and we'll start experimenting. We'll start small experiments on hardware. We'll generate pulse width values. After generating pulse width values, we'll check the hardware in a live video. So we'll take a break. After 10 minutes, we'll rejoin. After that, we'll start with the real hardware for this Simulink block. Okay.
Yes, sir.
ഒരു 5 മിനിറ്റ് ബ്രേക്ക് കൊടുത്തതാ സാറ്. ആ സ്ക്രീൻ ഷെയറിംഗ് സ്റ്റോപ്ഡ്. ശരി. ശരി.
Mohamed Aslam will soon join us with the hardware setup.
Hello. Let us start.
Yes, sir, you can continue. Yes, Mohammed, you can continue.
Okay, thank you.
Mohammed, yeah, you can continue.
Here we are having a hardware setup. We have connected all these things to the DSO. Actually, we have set up a converter hardware and a microcontroller. The microcontroller portion is connected to my PC. Then I will start with some experience. I will generate some PWM values. After that, we'll try to implement the control part that we have discussed in the simulation.
Aslam, can you please verify that it's not visible to some of the participants?
Please let me know. Actually, it is from another camera.
Yeah, but it's not visible.
Sir, it's not visible.
We'll check. We'll check. We'll check. I will share my screen. It is visible to my screen also. Please check. You can pin it. I think you can pin the screen.
ওখানে কিন্তু ব্যাংকের কোনো ডিটেইলস চাইনি ওরা তাও দিয়ে রাখা যেই
You can see something like this. You can pin.
See, all the participants are requested to pin the user inQbe innovations so that you will be able to see it very clearly. Participants, you may please pin the inQbe innovations user tab.
Please let me know after doing it. I will continue. Okay, thank you.
Yes, Aslam, you can continue, Aslam.
Okay, thank you. So we have connected these things to the oscilloscope. We have connected DC-DC converter, that is bidirectional converter. Now we have connected as it is the boost converter. And in black, we can see there is a microcontroller, and the controller is connected to the PC using JTAG emulator. I will show the picture of all this. So I will start with the PWM block. Actually, all these from the simulation, we have started progressively. First, we have done the basic converter. After that, we have added PWM. After that, we have added control loop. It is a progressive step. In similar way, we will have a progressive step to understand the things well. So I will start with the Pwm generation block. I will generate a PWM. After that, we will add all these things, all the things to the Simulink block, and we'll generate complete code. So I'll start with the Pwm generator block. I just added the Pwm generator block only. Here, I have set the value already. I have set the values to 20 kilohertz and PWM parameters to clear and set, and PWM-B. There will be two outputs are available, and one is set as clear and set, and another was set in set and clear mode. That is in complementary mode. So I'll share my screen also. Actually, you can see both my screens and the inQbe innovation screen simultaneously if it is needed. I'll set the PWM values in my screen, then we can see the changes in the hardware. You can switch into my screen also. So I'll share this Matlab screen also. So here in my screen, I have added a Pwm generator with a 20 kilohertz frequency, and I'll add a constant of here. I just add 30, that is the 30% value. Then I'll generate a code. I hope that my screen is also visible to you. Then in Matlab window, there is a button deploy to hardware. By using that button, we can generate a code. Now it is set to 30% duty cycle. So we should get 30 and 70. That the 70% is the complementary of 30 and 70% pulses for the Pwm generator. I'm just started the build option. In my screen, you can see that there is some files are generated. So from Simulink block, it will generate C files, and it will be translated into the binary codes, and it will automatically dump into the microcontroller. We can see that there is two pulses are generated. One is 30% duty cycle, and second is 70% duty cycle. So I'll do one more thing. I'll simulate this in live mode. In my screen, I have set this simulation to external mode, and I'm just running the simulation. That means the running the simulation into the hardware in live mode. I'm just starting it. The system will generate code and it will dump into the microcontroller. We can control the parameters from the Simulink block lively. This is a real-time Matlab real-time interface method. We can try this one. So we can change the parameters in live mode. I'm just waiting to complete the build option. It just started running in the hardware in external mode. From my screen, I have set the PWM value to 30%, and now I am just trying to change it to 40%. You can see the pulse width is varying. From live, I can set the pulse width value 40. I'm just setting it 20. And I hope that it is visible to you. Please let me know if any clarification in visibility or any thing to know. Let me know. I'm eager to know your response.
Yes, Aslam, it's very perfectly visible, and you are also perfectly audible. But the only difficulty, especially from those who have logged in from mobile, is that simultaneously they have to pin both the screens to get a clear understanding of it.
Okay, that's a limitation
Those
of
who have logged in from laptop, it won't be a big issue because while pinning those two, they will be able to see both the screens simultaneously.
Okay. Please do adjust with existing limitations. So I'll try to explain in detail. So now it is connected from the my laptop. It is running in live mode. That means from Matlab, it is connected to the hardware, and the control part is running inside the hardware. The set parameters can be changed from the hardware. Now it is only in open loop mode. We can set the pulse width value from the Matlab. Now we are trying to give it this to a converter. We will switch on the converter power. Now I have applied only 10%. I will just change the duty cycle. Now it is in open loop. I'm just changing the open circuit duty cycle value. We can see that from hardware screen, we can see the duty cycle is varying. It's only in open loop. That is, I am just giving open loop values of 30%. Now it is 17 volt. I'm just displaying the controllability. Just we can just control in open loop. We can apply 40%. Now it is 20 volt. We can apply 50%. Now to 24, I'm just going up to only 60%. Now it is close to 30 volt. I'm not going beyond this limit. Now I'm just sitting back to 50%. Now it is 24 approximately. Then we can see the variation. I'm just explaining the variation. We can set the pulse width value live from the Simulink. We can see the output is varying. I hope that it is clear. Okay. I'm just terminating this simulation. Then I will try to explain the PWM block, and after that I will go for control loop implementation, and we'll add ADC and all control loops. There is some noise coming. Please do all others mute. Thank you. So here we are getting a pulse width value that is set as the input of PWM generator. PWM generator block is inside the microcontroller that is connected with an external port. So we can control pulse width value from the code. So we'll add more things. Actually, in here it will generate pulse width value by having a counter. That means microcontroller is not having a great role in the PWM generation process. Only role in the changing of pulse width value. That means microcontroller is needed only when controller control parameters is to be changed. So controller will be free for the other process. That means a dedicated PWM generator block will generate PWM. That is very essential. That means if we need a much number of PWM, all PWM signals should be generated by Pwm generator blocks, not by the program. So we'll add more things. We'll add an ADC. I have an example. I will open that example. For simplicity, I'm just trying to add an ADC from here. Here we are having ADC that of 12-bit. Here I have applied 200 microsecond sampling rate for the control loop for ADC sampling rate. So now we can see the output of ADC by a display. I'm just adding a display block. From ADC, we will get the value of 0 to 4096. That's only counts. That we have to scale these values to voltage by giving a gain block. I'm just giving a gain block here to convert ADC value to the voltage. Here I'm adding a display block and a ray transition block for the display. Here I'm just giving a rate of 100 milliseconds. Okay, now again it is in open loop. There is a feedback and there is a control. There is a control. Pulse width value can be controlled and output voltage can be read from the display. So I will run it again. After that, we will have a control loop. I'm just trying to run it in external mode. This is being built and it will be transferred to the microcontroller. Just switching on the DC supply, we can see the approximate voltage from the ADC. Actually, in my screen, we can see that the output voltage can be read in display. It's almost similar to the reading from the multimeter. So I will just change the pulse width value. That means I am just trying to control by myself by giving pulse value, and I can read the values from the display inside the Simulink block. So now again it is in open loop, but there is a feedback that we can read the voltage from ADC. I hope that it is visible. If it is possible, please try to view my screen and the camera screen. Otherwise, I'll try to explain. I'm just giving the values from the Simulink block. At that time, the output voltage will be varied, and from Simulink block itself, I can see the voltage is varying. That's in open loop control and feedback. So we will add control loop inside this one. After that, we'll have a closed loop control. I'm just trying to add an error, reference and error block. From here. It is connecting to the Pwm block. This is the feedback. So I have set the output voltage to 20 volt. So the reference will be compare with the output voltage. The output voltage is getting from the ADC and the scaling factor. Scaling factor that we have connected because basically ADC input voltage is 3.3 volt. So the conversion from the count to voltage will be 3.3 divided by 4096. That 3.3 volt is upscaled to the higher value by adding a voltage divider resistor of 15K and 1K. That is R1, R2, that is 15, R1 is 15 and R2 is 1K. I have connected. So we will get the output value of 52.8 volt maximum. So we'll get a voltage that is connected to error section, then the PID controller that is taken from the simulation itself. So we have to get a control, closed loop controlled output from this simulation. I'm just trying to run it again. Now it is in closed loop control. We have added PID and reference voltage and the feedback along with the Pwm generation block. It's again building because it's need to convert several files. From the screen, from my screen, we can see that a lot of files, including C file, header files are generated. That will be translated into the binary code and will be fed into the microcontroller. Now we can see the closed loop output. We are getting approx 20 volt, close to 20 volt. There is some small difference between voltmeter and Simulink screen. That's due to calibration only. I'm just changing the reference voltage to 24. You can see it is getting close to 24 volt. I hope that you can see this. Now we will change the input voltage. Input voltage is varying. We can see that output is getting steady. Even input voltage is 16. And again, we can see the pulse width is varying when input voltage is varied. That means pulse width will be automatically adjusted to get set output voltage. All these are known to you, but I am just sharing this that can be implemented in the microcontroller. All the control system and control loop designs are done by you, most of you, and all those PWM closed loop control can be implemented using a microcontroller for a DC-DC converters. I hope that it is visible to you. For continuing, I need some response. Actually, if anyone having any
yes,
queries,
Aslam, it's perfectly visible. Participants, please respond to what Aslam is asking.
Yes, sir, visible, sir.
Yes, sir, it is visible.
okay, thank you. If anyone having any queries about this hardware, actually, because of the time limitation, we are skipping several steps. If anyone having any queries for implementation, please let me know.
You so much. We cannot solve our problems with the same thinking we used when we created. This is the statement of Albert Einstein, and this should be the.
Participants, if you are having any queries, you may ask to Aslam now. Regarding the simulation, if you are having any queries, not only regarding the software development, even regarding that hardware portion also, if you are having any doubt, you may ask. Aslam, hope everything is clear for them. You can proceed.
Okay. Thank you. Actually, I'm stopping the simulation. If anyone having anything to apply in hardware, I will change as per your request. If anything is to be added, actually from this, actually we have just added a rough design. We have skipped the design in this one. We have just applied a rough values for the converter design and control design. Because of that, we will have a lot of limitation in the dynamics of all these control loop. So if we design the system very well from the converter design and control design and the programming, we'll get a perfect output as we decide in the design, total design. So similar way we can implement other controls, just like motor controls and other controls by using STM32 microcontrollers in similar way. Here we are discussing only the way how we can realize the hardware with simple way, that because we have been using this one for several years for our experimentation and R&D purpose. Because in my experience, we have interacted with a lot of educational institutions, especially in KTU and other state colleges. In most of the cases, we have a lot of limitation actually due to our system and a lot of other limitations. We are facing difficulties for implementing hardware. Actually, in some cases, hardwares are available. In some places, hardwares are available. Only control scheme implementation difficulties are facing. So we are sharing our experience in industrial implementation with the academic institutions and faculties. Especially, we are focusing faculties only because student interactions cannot be long lasting. Actually, they will learn and they will go for industry. But even if we can give maybe our experience to faculties, they can continue using this one for long run. So I'll continue with my explanation of this. I'm just stopping the video of hardware. I hope that my PC screen is available to you. And we have used this converter with but actually this is a bidirectional converter. From one side to one side, while on another side can be used as a buck, and from here to there we can use as a boost. That means it can be worked as bidirectional converter. It is a synchronized buck boost converter. In both cases, it can work as a synchronous converter without having loss of diodes. So we have used IR2110 drivers for the driving MOSFETs, and it is connected to the microcontroller that we have seen in the hardware. And this is the TMS-T20 controller board that we have used in our lab that has been developed by us. This is especially for academic and experimental purpose. That control loop already we have implemented like this. I'll try to explain about it more. Actually, three parts are there. One is the control part, that is the code that will take care of the execution, and other part, the dedicated hardware, just like ADC and the Pwm block. By clubbing these three things, our control algorithm can be implemented. As I said, we can implement controls like motor control, like BLDC, PMSM, and induction motor, and we can control grid connected inverters and similar restart comps, and all these things. Digital control can be implemented using sufficient controllers. In different application, we may have to use high performance controllers. Here we have used the TMS-T20-28027. That's a starting device that not having floating point computation. That's only having fixed point computation. If we need a higher capacity, we will have higher capacity microcontrollers with floating point capability and frequency up to 200 megahertz. Currently, we are using a TMS-T20-280-379 microcontrollers for higher computation applications. These are the blocks we have configured for PWM generation. I will share the slide with FTP organizers. If you need, you can download it. This is the PWM generation. I have already discussed it. PWM generation is done by the counter and compare unit inside the microcontroller. In most microcontrollers, there are PWM generators, but in different controllers, features will be different. For example, if we need a dead time, that means if we use a complementary MOSFETs, upper and lower side MOSFET, half bridges, we will need a dead time that can be programmed inside the PWM generator here. In normal controllers, just like Arduino and other controllers, does not have the features of things like this. And in TMS-T20, there are a lot of features, just like phase shifted PWM can be generated, and frequency controlled PWM can be generated for the different applications. ADC that we have connected by using our resistor network to reduce the voltage towards the microcontroller. That means microcontroller will receive only 0 to 3.3 volt linear, but when we need a high voltage, that is especially in this application, that is we have scaled to 52.8 volt, that can be downscaled, just like we are downscaling the voltmeters. Lower voltage voltmeter range can be extended to higher voltage by having resistive dividers. In similar way, we have used resistive dividers to reduce the voltage towards the microcontroller. And PID controller, we have translated PID controller that is already available inside the Simulink, but even in the block inside the Simulink itself having lot of features internally, just like anti-wind-up scheme and upper lower saturation limits. All these things are available inside the PID blocks that will be translated into the code without having much programming complexity. That means, I'm repeating this, we can avoid programming complexity if we have an algorithm in Simulink that can be implemented to the microcontroller. And this is an internal block of PID controller. As we know, there is proportional control and integral control and the derivative control. In proportional control, there is only a gain, but in integral control, there is option for anti-wind-up scheme inside Matlab that we can use. And derivative control, we can have a filter to avoid high frequency noise. All these things will be automatically translated to the hardware. So when we write a code manually, all these things will be coming to the picture. In coding, there are there are a lot of challenges when we write code manually. When we look into the PID controller, integral and derivative control is based on time, that is time dependent control. So it should have a proper control loop sampling time. So the sampling time should be maintained by scheduling. The scheduling is done by timers and interrupts in the microcontroller. In Matlab Simulink based code generation, it will be automatically done by the code generation block. That means scheduling will be automatically calculated and translated by the coder. When we go for normal coding, we should have to configure timers and interrupts to make a scheduler block. In most of the controller, it will be very difficult because we need to learn the controller architecture entirely. And about the sampling rate should be considered because higher sampling rate will be tough to execute by the microcontroller. Higher sampling rate normally is good, but ideally it is good, but practically controller cannot follow that sampling rate. So system will lag That means if we implement a 50 hertz inverter, if it is lagging, we will get a frequency lower than 50 hertz. It cannot go real time. So sampling rate should be taken care when we are going for the hardware implementation. And data type, when we need a computation, there will be data type just like integer, float, double precision floating points. We should take care of float data types to reduce the computation complexity for the microcontroller. Hardware implementation that we have discussed, simply we can download the Simulink block to the hardware. In similar way, we can do hardware implementation even in Arduino also, and DSpace, other controllers just like DSP, and in some microcontrollers there are features to implement Simulink blocks to the hardware. Normally we have used digital control implementation, so error control loop error will be very less. That means control loop variations, time and other age variations will be less. If we use analog control, there will be aging issue and other environmental issue will be affected in the controller. But because it is digital control, there will be less impact of noise in the control loop. And we can use microcontroller or Fpga for the digital control. For normal lower speed application, medium speed application, we can use microcontrollers. But for a higher speed application, we have to go for an Fpga. Similar way, we can use Fpga code generation, just like Verilog HDL code generation feature from the Matlab. Digital controllers, normally we use Texas Instruments C2000 family microcontrollers and the STM32 microcontrollers. For industrial application, we use STM32 controllers. In older projects, we have used DSP microcontrollers, and FPGA we use Xilinx FPGA series. Simulink coder, in similar way, we can implement inverters from the Simulink to hardware. We have done several experiments in motor control and inverters, and we have conducted several direct FDPs regarding this. Simulink coder process is like this. Simulink block will be translated to C program, and it will be converted into assembly language program, and again it will be converted into the machine code that will be loaded to the microcontroller. That means in older microcontrollers, we have used assembly language program, and nowadays we are using high-level C, other languages, and now we have another step. We can generate C program from the Simulink block. So one level is up. So complexity will be very less. That we have discussed. I'm just trying to make it clear. We can use the deploy to hardware button from the Simulink block, that we can translate these things to the hardware by simply clicking. All the things will be done automatically. We have to set only the prerequisites are we have to install the required softwares from this Matlab, and we have to install the software from Code Composer Studio from TI. All these things should be pre-installed before building. When we install all these things, we can build the code by simply clicking. Things that I have already discussed, data type and model should be the continuous model cannot be translated. That means when we go for a PID or integrator or something, it should be discrete mode. And sampling rate should be taken care, and mathematical complexity also and execution load also should be taken care. When we go for fuzzy logic type, computation complexity should be taken care. And hardware experience. Actually, this is to share my experience with interacting with education and something. When we try to find some hands for a hardware project, it is very difficult to find someone for a project development. Actually, when we think about a new project, there should be a new team for that. Actually, when we try to recruit a team, actually we are struggling even we try a lot of numbers, it is tough to find a good hand for the hardware. Because actually we are not having proper setup for hardware experiencing. In some universities, actually they are not giving much importance for the lab. But nowadays, actually we are realized all the needs actually for the hardware. Actually, when we discussing about the EV charger implementation, we can see that most of the hardware, especially in fast chargers, are coming from China. That means we are installing most of the chargers here. Its internal part are coming from China or other countries. Actually, we are having very less facilities for providing hardware support. Most of the projects are coming from Chinese clients, Chinese providers. So actually, it is a very dangerous situation. Actually, we are losing a lot of money, and we are losing a lot of opportunities, and our students not having core job opportunity, that is having long benefits. But we should more concentrate on hardware implementation also. Projects, I'll discuss some projects that is being done by inQbe Innovations. Actually, we are working on, actually we have worked on BLDC controller. This is the BLDC motor and controller that is designed for EV application, EV traction application. This is a 2 kilowatt motor and a controller. Controller was programmed by, used by STM32 controllers. And control algorithm was developed inside the Matlab, and we have in this case we have done the code manually to make it efficient, because we have need to use lower price microcontrollers for this application. So this code was written manually, not by Matlab. And another project was the PMSM controller in similar way, but it is in hardware structure is there is some difference. But PMSM FOC controllers, in this case we have used the TMS T20 controller for experimentation purpose. It's 5 kilowatt capable hardware that's it's being tested in our lab. This is switched reluctance motor. Nowadays SRM are coming into the picture when EV productions are in progress. So we have worked on switched reluctance motors in some cases. Same TI controllers were used for control implementation. This is a DC-DC controller that we have discussed. This is for experimentation purpose only. That's for not for the commercial application. And we have worked on a battery management system. That's work is being done. This is a development board only from a linear technology. We are working on 24 cell lithium battery management system for this. And the other things we are working on chargers and PF correction and isolated converters and vehicle communications. And major things that we can work on it actually, that is MOSFET, IGBT, silicon carbide device, and GaN FET devices we are working on. And driver circuit, that most of the driver circuit, popular driver circuits are imported from other countries. Actually, we are working on IGBT drivers also. And the protection is the main fact actually. When we go for hardware implementation, there will be a lot of challenges in the device damage. So protection circuits we are already developing. And PWM and digital control that we have already discussed. And I'm expressing my thanks for hearing us. So I'm just switching back to
Yes, Aslam.
If anyone having any suggestion, any queries, please let me know.
Yes, participants, you may please raise your queries.
Aslam sir, good afternoon, sir.
Yes, good afternoon.
Your presentation is very informative, and you have explained every slide very clearly. I'm having a small doubt. Instead of that conventional PID controller for the same circuit, for the same setup, can we use fuzzy PID controller, sir?
Yes, actually, for same setup, we can add fuzzy block and simulate. After that, we can translate fuzzy blocks to the hardware. But only thing is to be taken care. Fuzzy conversion will need a lot of memory. So higher memory device should be used.
Okay.
Okay.
Sir,
That's
further,
an
if
important.
we need any explanation, that means if we want any information, shall we contact you, sir?
Yes, we are welcome. You can contact me. I'll share my email ID in chat
Okay,
box.
sir. Thank you, sir. Thank you very much.
Sir, in battery management system, which parameters actually you are tracking on hardware?
In BMS, actually, we have first thing we have in cell balancing. In the project I have explained, that is, we have used passive cell balancing, and we are working on active cell balancing also. And we are tracking SOC and temperature and SOH.
Suppose battery charge 18% and it will go say 8 kilometers or 10 kilometers.
Sorry, I didn't get you. Actually, there was some break in your voice.
Suppose state of charge is 70%, and in 70%, how much kilometer electrical vehicle will travel? So how we can find it?
Actually, that we can find by the average vehicle efficiency. Actually, 70% charge is only indicating this level, but a percentage should be converted to energy. That means based on battery capacity, we have to convert it to energy. Suppose 70% means 7 kilowatt out of 10 kilowatt. That based from 7 kilowatt, based on the driving practice of the driver and vehicle and efficiency, we can calculate distance. That's the way on we can calculate. Thank you.
Yes. Any other queries from participant side? Gulshat Sheikh sir, can you please give your feedback to Aslam sir? Aslam, many people are actually commenting on the comment box that it's very informative session, okay, but they are not ready to come forward and give a feedback. I don't know why.
No problem.
Ashwin
okay, sir, I am giving, sir. I am giving, sir.
Come forward, yes.
Someone else is want to talk?
No.
Okay, myself, sir, Dr. Asha Shendge. Can you hear me properly, sir?
Yes, I can hear.
Sir, actually this session which is showing hardware and software combination simultaneously and working together for the controller and all is very good. Means up to now all the sessions we have not seen this kind of a presentation, sir. All the sessions were either theoretically emulative time. Yesterday also one Arth Patel has shown some part, but that was for the different type of software and all. So this is really helpful to understand the things. What happens now, electrical vehicle is our, we can say this, as a faculty, we want to do research, innovation in this, but till our idea is very in an initial stage only. So looking the hardware, software combination together, it definitely helps. We will contact you, sir, for further guidance, because all the PhD students also and MTech students all are working on EV only. So we will definitely seek guidance from you, sir. So thank you very much, sir, for your presentation. Good, very nice presentation.
Thank you.
Sir, can I speak?
Yes.
Actually, I wanted to. So actually, the presentation was really nice, and in fact, I felt like I am attending FDP offline.
That's good. Thank you.
So thank you so much, and just a request: can you share the video of your project, like the display which you have given today? So can you share that video of that display?
I'll try to make a video and share with the FTP coordinators.
Yeah, fine. Thank you so much.
Thank you.
Sir, Mohamed Aslam sir is asking to share your contact, please.
I have already shared. I will share my email ID and phone number.
If possible, please share it in the chat box now.
Yes.
Shall I share my email ID on chat box?
Yes, no problem.
Okay, thanks, sir.
Yes, with that, we are concluding our program. Yes, Sabira, ma'am. Yes, Sabira.
Yes, actually, first of all, I would like to use this chance to thank the coordination team behind this program. Thank you, Mr. Renu and team, actually, for selecting such a relevant and trendy topic for our FTP. Thank you very much for such a relevant topic for our faculty development program. You have arranged highly expert resource persons for every session. That's why all sessions were very useful and informative. So regarding our session, as all says, this session is also very useful, very great, very informative session. Thank you, Mr. Mohamed Aslam, sir. And actually, I have one doubt. Actually, we know in control system, actually, regarding that controller, okay, PID controller. Actually, I know there are various advanced controllers other than PID, but why still PID controllers are used in such? Even now, why PID is using the
Actually, that's a very important question. Actually, there are a lot of other control experts are also available in our academic field. But I'll explain from my point of view. Actually, there are a lot of other controls are coming. Some are more intelligent than PID, and some are less intelligent than PID. But PID is an evergreen control. But it is started from early stage, but still it is used in industry because its simplicity and the performance based on other things. It cannot be directly replaced by other things. Even it can be advanced by adding, just like a fuzzy PID can be improved. Its drawbacks can be improved by adding fuzzy to it. That will give more advantage. That's a thing behind it. I understand. But control experts are there, they can answer this very well.
Okay, sir. Thank you. Thank you for the reply.
Thank you.
Any other queries from participant side? Okay, Aslam sir, just like what participants have said, you have combined both the simulation and hardware, and this is in fact the first presentation which we all were getting like this. Among the 14 sessions, only one session we have seen. Actually, I can say that this session is purely carved for the faculties, because all other sessions, the people were from different industry sides. But in your case, you are a training person and you have given us training in the best manner. In a very excellent manner, you had given us the training. A special thank you for doing such a wonderful session on behalf of all the participants and from College of Engineering, Tadashiri.
Thank you. Okay, thank you. Shall I leave?
Yeah.
Okay, thank you.
Yes, participants, we have completed the last session of the day. In fact, the last session of program. We will resume at 2 o'clock for our validatory function. At least I request some of the participants to step forward at 2 p.m. and give your feedback genuinely. Then around 2:15 or 2:20, I will be sharing the link for taking the assessment. Then you can take the assessment and you can leave. Please don't forget to give the feedback on AICT Adal portal by logging in as a participant, and you shouldn't forget to give the feedback there for this particular FDP. Then only the certificate will get issued to you.